My name is Andre Leday, and today we're going to be talking about the Clapeyron experiment, which is experiment number 1 with respect to the bracket experiment we did last week. So first off, we'll start about talking what is the Clapeyron equations. They pretty much represent an important relation involving the saturation pressure and temperature, and the change in entropy associated with the change in phase, and the specific volumes of the two phases. So in particular, it is an example of how a change in a property that cannot be measured directly can be determined from measurements of pressure and temperature. So this is the basic equation, the general form of the equation we're going to use. It says that the change in the saturation pressure over the change in temperature equals the entropy of the vaporization over the specific volume of vaporization equals what we're going to be trying to find in this experiment is the latent heat of vaporization, which is the enthalpy of vaporization, over the saturation temperature multiplied by the specific volume of vaporization. So that's going to be our main objective, is trying to determine this latent heat of vaporization for multiple saturation pressures and temperatures, and then verifying these results and comparing them to steam tables. The goal is to understand the relationship between these properties as the liquid changes phase through vaporization. So this is pretty much the basics equation that we're going to use in the calculations. And all I did here was substitute using the ideal gas assumption, substitute the specific volume of vaporization with using PV equals RT. And we get this subsummation of the latent heat of vaporization times saturation pressure over the saturation temperature squared times the ideal gas constant. So for setting up the experiment, this is the basic layout. We have a 1 liter flask, which is 1 with water in it, over a heat plate, and 3 is pointing to a K-type thermocouple that runs through the PDAG acquisition system software in the computer. And we have up at 4 an analog pressure transducer that runs off the PDAG software, and 5 we have a mechanical pressure gauge. So at 6 you're going to see an air bleed valve, and at 7 is the vacuum control valve, and down at 8 is the centrifugal pump, and 9 is the reservoir of water. So for setting up this experiment, we're going to first open the PDAG software and open that Clapeyron.cfg in your browser, and you're going to want to configure a few settings. So you're going to want to set the thermocouple to the K-type, 25 millivolts low noise settings, and the pressure to auto volt setting. The pressure is going to be recorded continuously the data is going to be recorded continuously for the 5 to 10 minutes it takes for the beaker to heat up, and it's going to take data points every 2.5 seconds. So you're going to verify the DAX system records the data correctly before you start by just looking at the computer and seeing that the pressure and temperature are at ambient conditions. Then the test can be ran with or without boiling beads per instructions from the instructor. And pretty much what boiling beads do, they're just like these black, porous, rough beads that you can put in the water, and they prevent superheating and will provide a more controlled boil. So he's going to tell us if we should use that or not. So we're going to fill the beaker up with 2 inches of water, and the thermocouple tip should be submerged 3/4 of an inch. And then we're going to make sure the inlet and outlet of the pump are submerged, because you don't want to run it dry, and turn the pump on. Make sure the vacuum control valve is open, and verify air is being drawn in, and you want to leak test the system. So going back to this, the way you want to leak test the system is you want to close the air bleed valve, and when the pump is on, and you're going to see that the stopper in the flask is going to suck in, and you want to make sure that the mechanical or pressure gauge shows that the pressure is going down to almost zero. And then once it gets to almost zero, you're gonna shut off the vacuum control valve, turn off the pump, and you want to see that the gauge is reading that it's about zero or staying at a constant pressure. So then we're going to get into the experiment once the setup is done. You're going to want to turn on the vacuum pump and bring the flask to the lowest possible volume, lowest possible pressure, and leave the vacuum control valve open. You're going to want to turn on the hot plate to the hottest setting, which is the high setting. Begin logging data after the water starts to boil, and make sure the thermocouple doesn't touch anything besides the water, or you don't want it to touch the boiling beads either. Next, the pressure needs to slowly equalize in the flask. So to cause the pressure to rise, you're going to slowly close off the lines of the vacuum pump. Then you're going to want to keep an eye on the saturation pressure and temperature periodically during the experiment. And before the pressure in the beaker reaches atmospheric, you're going to open the air bleed valve to avoid positive buildup. Now, after the water reaches a rolling boil at atmospheric pressure, you're going to want to stop taking data. And for shutdown, you're going to want to turn off the hot plate. Well, first make sure that you can let the beaker come to cool down a little bit, and turn off the hot plate, close the vacuum control valve, open the air bleed valve slowly, and turn off the pump and disconnect the power supply. So this is pretty much a chart for the pressure versus saturation temperature for water saturation and for vaporization. And so what you're going to want to do is, for 3 arbitrarily chosen pressures, you're going to be able to use the modified Capron equation to solve for the latent heat of vaporization, and then compare your results to those steam tables. A couple notes when you analyzing the results of the experiment. When you're looking for the change in pressure over the change in saturation temperature, you're going to want to curve fit it as an equation and then take the derivative instead of just calculating it directly from the set of numerical data you get. And then you should be able to estimate the amount of air introduced by invoking the ideal gas constant into your uncertainties. My predictions is that when you have a lower pressure in the flask, it's going to lower the energy needed for the water to boil. So the water should boil, boiling point should be lowered. So as the pressure equalizes the atmospheric pressure, you'd see that it's harder for the water to boil as it comes to atmospheric pressure. My suggested improvements, obviously we haven't done this experiment yet, so I'm not exactly sure what could be improved. It looks, thermocouples hold in place, should be in the same place at all times, about 3/4 of an inch, as long as everything's followed pretty exactly. Everything should be controlled. Do you have any questions?